So, anybody still not too tired to listen? So we talk about why computers calculate wrong. Let's see. So anybody has heard about the, doesn't like me? No? Then we have to use my own. My works. Sorry for the delay, guys. I know it's already late, but talking only the first slide all the time is not such a good option either. So let's see if it works now. Yeah. So anybody has heard about the year 2000 problem? So at least the guys who are as old as I am. So that's the question: how many digits has a year? And then the next question is, how do you use integers in your program? Anybody uses int without thinking much? Okay, so I hope you won't do it anymore after today. So here's the quiz. So we have this int, that's something, the biggest thing that you can put into an int, and then we add it with itself, we multiply it with itself, and then we get the result. So what's our result? Let's find out. Something like that. So it's not really what our math in school was, at least for the one who still remember, for the younger ones, but that's what we get. So the reason is that this int is limited to a certain range. We can't go beyond that. That's maybe okay, but it's worse than that, because it has a weird behavior. When you add something big to something big, then you get something small. So, what's the idea? The idea is something called modular arithmetic. So, plus, minus, and whatever we use, they are not our mathematical plus, minus from school, but our modular mathematical plus, minus from school that we use when we do like algebra in university. And it's something weird, but it's not so weird. Has anybody seen something like this? And it works like that. When you have 11 o'clock and then you go 11 hours later in the 12-hour clock, so for the Americans where you have only 12 hours, you get something like 10 o'clock, or you get 22 here, but then when you go 22 hours later from 22, then you get something like 20. So you see the principle. And that's the idea. So we can rebuild them. I think it's too late to look through code like this, but you can trust me, I tried it and it compiled, and some years ago it even ran. And so I just simulate the behavior of this modular arithmetic with some code. So when we run this thing, we get the same result. And that's the point. So the weakness of int, and actually long as well, even though long is a little bit nicer, but not really, they overflow, but they don't tell you when they overflow. They just do it, and you just don't realize. No exception, nothing. So how you address it? So there is one way, and we are lucky in Scala. This way is not so painful as in Java. We can use something called BigInt. And BigInt just expands the number of digits, and then we just get correct results. And the important thing is always think about the possible values. Never, never, never forget it. Because when you use int for money, for example, and then you have hyperinflation, and then suddenly, okay. And always think about intermediate results. So the good thing is we are using Scala, and we have this BigInt, and it works with plus minus because we have operator overloading applied properly. So it's kind of good. Now the question is, who uses ever floating point arithmetic? Who has used the double in the last 10 years or so? Oh, okay. So then you still might stay because the rest is about double. So we have this quiz. We take 1. And then we divide it by something very big, then we add 1, then we subtract 1 again, and then we multiply by something very big. And so, what do you think is the result? Who has any idea? Yeah, you got it. So it's 0 because we have only limited number of digits, precision, and then the significant digits that are actually our information, they just are thrown out because we don't have so many digits. So the question is, how can we deal with this? And this one is not so easy to deal with, because if you have like trivial examples like this, we can figure it out ourselves. But if we calculate, for example, a bridge or something like that, then we should really get people involved who know this area, because it's not something that you learn in 5 minutes. Sorry, I don't know it well enough either. So I would have to get somebody as well, at least for a bridge that I would dare to cross myself. So that's the thing. But for easy examples like this, we can just think ourselves what would happen there, and maybe take extreme values and do things like that. The good thing is sometimes we can just go to big int or long, because we just use the double of in terms of laziness. For example, if we use money, yeah, and then you have like euro and cent, or dollar and cent, and grivna and 100 of a grivna, I forgot what it's named. Kopek, może być, da? Yeah, and then you can just use double out of laziness, but that's not good. Use the kopek as unit, and then use long or use big integer. And then you are on a good side. And more often than not, you can just get rid of double, unless you're locked in with a language like JavaScript, where they force double on you. But we are working with Scala here, so it's good. Yeah, and another way is to go to rational, actually. And there's the spiral library, and you can find functions. So it's fractions, like 5/3, something like that. And you can do a lot of things with that, and that is very accurate. It has just one very ugly behavior. If you do real calculations with it, with each step, the length of the denominator and the numerator double. So when you do like matrix calculations, then you get swapping of the disk, because this matrix, the numbers of the matrix already use up the memory of the computer. So it's something where you don't really get very far, but sometimes it can save your ass. So that's this thing. Or you can use this thing BigDecimal. And BigDecimal has arbitrary precision. It gives you explicit control of it, but it's a lot slower, and it is kind of bypassing all the speed that we have in the hardware arithmetic, because it does all the thing by hand, and it forces decimal system, while the computer is optimized for binary system. But it does help us in many cases, especially if we deal with money. Problem, at least with the one that we have here, they don't have functions like exponential, logarithm, sinus, cosine, and whatever you like to deal with. So that's that. Another interesting approach is to use intervals. That means that you calculate everything and do the upper rounding and the lower rounding. And then you have an interval, and you know the exact result is always in the boundaries of the interval. And at least you get a warning when this thing runs in weird ways, because then the interval length gets very long. And then you know, well, you can throw away your result and rewrite your program. I guess that's in areas where you should get people involved who know integral arithmetic, but it's an interesting and useful way to go. Yeah, we have another quiz. So we do this double 0.2. It's a very accurate number, yeah? And then we try to convert it to a string, but hex string. It's possible to do that. Who has an idea what we get? Well, let's find out. You get something like that. Why do we get something weird like this, and don't get 0.2 or something more reasonable? Let's see. The reason is, in decimal, we can express things like 1/5 or 1/8 or something like that very good. And what do they have in common? The they have in common that they are the denominator, the thing on the bottom of the fraction, is you can divide a power of 10 by this thing. You just have to go to million, 10 million, whatever, and divide this 10 million by the thing on the bottom, and you get the integer number. And 5, 25, 125, they all work if you just take a long enough power of 10. But now, when we go to binary system, it only works with powers of 2. So 5 is out of scope already. And it's not such a surprise if you think 1/3 or 1/7 or things like that. You can't express very well in decimal system. So 1/5 in binary system behaves like 1/3 in decimal system. So that's not exactly expressible. So that's the point. We have to think that everything that's not with power of 2 doesn't behave so well as we would like. So that's what we saw already. And how do we deal with it? Well, when the decimal is part of our logic, when we calculate bridges, it's not a part, it's quantities is our logic. Yeah. But when we calculate money, then maybe the decimal, if we just don't forget the trick with the integer, yeah? If we just for the moment think, then decimal is actually part of our logic, of which think of exchange rates, yeah? You have like 1 euro versus 1 hryvnia is certain exchange rate, and they give you the exchange rate with 6 digits after the decimal point. But that means this is a legal bounding rule. It's exactly like this, and it's not kind of like this. And you have to do the math with this. And then decimal is part of our logic. And when decimal is part of our logic, then we should use BigDecimal. That's it. Thank you. Any questions? Okay. Thank you.
Thank you.